I'm Professor Melko, Chemistry PhD, and your university chemistry professor. And today we're going to classify compounds into ionic compounds, molecular compounds, and acids, and then learn how to classify cations, positively charged ions, and anions, negatively charged ions. Enough with the introduction, back to work.
Get back to work, you slacker.
So, let's start by classifying compounds. Okay, ionic compounds are one type of compound, and we'll see this means that you have elements from the left side of the periodic table, a metal, getting together with elements from the right side of the periodic table, non-metals. Okay? In terms of these ionic compounds, you can have two different types of ionic compounds. Binary, which means two, and ternary, which implies three, and sometimes more than three. Okay? So binary implies two, and binary ionic compounds are then made up of two elements. So some examples here are sodium chloride and aluminum chloride. Again, notice that for ionic compounds, it's always a metal, like sodium, with a non-metal, like chlorine. Something from the right side of the periodic table with something from the left side of the periodic table. Sorry, left side for sodium, right side for chlorine. Okay, you can also have these ionic compounds come as ternary, right, which implies three. And so these have three different elements. So now, in addition to a metal like potassium and a non-metal like nitrogen, you have perhaps another non-metal like oxygen. Okay, so at least one metal and one non-metal, because it has to be that for ionic. But then you have this third element. So that's classifying ionic into ternary and binary. We can also have molecular compounds. And for these compounds, at least for the purposes of this lecture, we're just considering binary molecular compounds. Okay, whereas we had ionic being a metal and a non-metal, here binary molecular compounds are just both non-metal. Right, so these are both elements that are nonmetals. And most of the nonmetals, of course, are on the right side of the periodic table, like nitrogen, carbon, oxygen. Hydrogen sometimes is a little bit different. It's placed on the left, right, because it has that one valence electron, but it's still a nonmetal, right? So don't be confused about that. So here's some examples. NH3, CO2, H2O. These are all molecular compounds. Why? Because they're only nonmetals, like carbon and oxygen, right? Like sulfur and fluorine, for example. Okay? They're all binary here because there's just two elements in those molecular compounds. So that's ionic and molecular. We also have acids, okay? And aqueous just means dissolved in water. So these compounds, these acids, are always going to be denoted with this phase of matter. So we can have solid, liquid, gas, but we can also have aqueous. Okay, all of our acids are going to be aqueous, which means those compounds are dissolved in water. So water is always around these acids. We can have two different types, just like ionic, binary, and ternary. Okay, binary acids, two elements. One of them is always going to be hydrogen. So if it's an acid, it's starting with H. Okay, so that's one of the telltale signs that you have an acid, is that hydrogen is the first element. It's not always going to be that case, right? You can have things that begin with hydrogen that are not necessarily classified as an aqueous acid, like water, right? But a lot of compounds that begin with H will be classified as an acid, like this hydrochloric acid or hydrofluoric acid. These are all binary acids because it's just H and one other nonmetal. Okay? Ternary acids, and sometimes called ternary oxyacids, are going to start with H as well, but the oxy means they're going to have oxygen. Ternary means there's three elements, so there has to be one other type of element, and it's some other nonmetal. So here for nitric acid, it's nitrogen. For sulfuric acid, it's sulfur. Right? But recognize these things always start with a hydrogen, so it's an acid, have oxygen, so it's an oxyacid, and one other nonmetal, so it's ternary oxyacids. Okay, so those are really our three divisions of ionic compounds, molecular, and acids. Let's do some practice problems to really reinforce these concepts. Okay, so let's classify the compounds listed here in one of these categories. So let's consider first calcium oxide. Calcium, I'm going to look on the periodic table and identify that over here as a metal, right? And oxygen as a nonmetal. So I clearly know this is ionic, right? Because it's a metal from the left with a nonmetal, which is on the right, okay? So this calcium oxide is clearly going to be ionic, but I want to do better than that. Is it binary or ternary? It's clearly binary. There's only two elements. So binary, ionic. On to the next one, sulfur dioxide, SO2. Let's find out where those are. I'll circle these. There's sulfur, there's oxygen. both nonmetals, so this must be molecular. 2 elements, so sulfur dioxide here is binary molecular in this case. And classifying these things is going to be important when it comes to naming them, right? So the different types of compounds, ionic, molecular, and acids, all have different ways that you name the compounds. Okay, that's why we're dividing them up before we learn the rules in the next lecture on how to name these things. So SO2 binary molecular. Move on to the next one, silver chromate. Well, now we have 3 elements, but let's classify where they are. Silver right here, chromium right here, and oxygen again over here. Every compound thus far has had oxygen in it of these practice problems. Okay, so now we have 3 elements involved. There's some metals with nonmetals. That, of course, triggers our brain to say ionic, metals and nonmetals. And there's 3 of them, so this is going to be ternary ionic. And lastly, hydrobromic acid. I mean, this is kind of a giveaway because I'm writing acid here in the practice problem. But even if it didn't have this written and just said HBr, that certainly has the look of an acid. It starts with hydrogen, as all acids will, and then it has this nonmetal bromine. Okay, so this is going to be our aqueous acid. And that's it. That's how we classify these compounds into these different categories. Right? And you can see the naming conventions for these are a little different. We have oxide, IDE. We'll see that becomes important in naming ionic compounds, right? Versus silver chromate, right? Which has something to do with the polyatomic here, CrO4. So all of that in the next lecture. For now, we're just classifying these things. We can also classify the type of ion. Remember, an ion is a charged particle, right? So you can have an atom, certain number of protons with electrons around it. And if the protons and the electrons are equal, it's a neutral atom. But if I remove one of those electrons or add an electron, now there's an imbalance in the positive and negative charges, and so that the atom is charged overall, we call that an ion. A positive ion is called a cation, not a cation, right? This is a cation. Okay, so think of, an actual cat when you're pronouncing this, a cation, and this is an anion, right? An kind of looks like anti, right, which sounds negative. So our negative ions are anions. So we can have positive cations, negative anions. Elements on the left side of the periodic table, right, these metals tend to lose electrons and form cations. Elements on the right, like chlorine, fluorine, oxygen, tend to gain electrons and form anions. And this is, of course, related to their efforts to get to this noble gas configuration that we've talked about in previous lectures. So feel free to go back and watch those videos as well. Right? The elements on the left side need to lose electrons to achieve that noble gas configuration, so they become positively charged. Losing electrons is losing negatives. Right? Elements on the right side need to gain electrons to get to the noble gas configuration, so they gain negative charges and become negatively charged, or anions. We also can classify these as polyatomic ions, right? When there's groups of atoms, right, that together gain or lose electrons. Okay, so polyatomic is when you have groups of these things. When it's just the singular element, like fluorine minus, this is monoatomic, mono for one. So one atom versus poly, many atoms, right? And the charge here on SO4 2 minus is over the whole group of atoms, not just on the oxygens, okay? So that's what makes it a polyatomic ion. Okay, we can look at one other thing, which is the size of these atoms. Okay, so consider our sodium atom, which might be this size, right? There's some protons in here in the nucleus, and there's some electrons out here. And we know they're organized in shells, right? And maybe there's 3 shells with different numbers of electrons in them, of course. But for the purpose of this, I'm just going to draw these 3 shells. So if it becomes sodium plus, I remove one of these electrons, the outermost electron, and so this atom gets smaller. Okay, so the point I want to make on this slide is that when these atoms become positively charged ions or cations, they get smaller. Why? Because you're removing these outer electrons, and now the atom is smaller, right? I've removed this ring of electrons, so the size of the atom is now smaller. Right? You can contrast that with a chlorine atom. Again, there's a bunch of protons in here. There's some electrons out here. If I'm going to add more electrons, right, they live further out. And so this atom gets bigger. Okay, so the takeaway here, now that they're learning something about ions, is that anions are larger than the neutrals. Cations are smaller than the neutrals. So sodium is bigger than sodium plus. Chlorine is smaller than chlorine minus. Okay, just to relate back to our concepts of atomic radii from previous lectures. Let's try to classify these two ions. Okay, barium ion. There's only one atom here, so it's monoatomic, sometimes just called monatomic. But this barium 2 plus is clearly one atom, so monoatomic. And now we ask ourselves, is it positive or negative? It's positive, so that's a cation. Carbonate, our other example here, well, there's more than one atom. It's a group of atoms, so that's clearly polyatomic. And it's negatively charged, so I'm going to call that an anion. Okay, now we have ways of naming these positively or negatively charged ions. Right, so we've classified compounds into ionic, molecular, and acids. We've then further categorized ions into positive and negative, and now we're going to name the ions. So in naming the positively charged ions, or cations, it's pretty straightforward. The name of the ion is just the name of the element plus the word ion, right? So magnesium, the element, becomes magnesium ion. Sodium, the element, becomes sodium, the ion. Okay. Most of these elements on the periodic table, or I should say on the left, these two rows, right, and several of these that are going to form positively charged ions, right, just get the word ion: magnesium ion, beryllium ion, potassium ion, aluminum ion. Some of these further down ones don't quite qualify, but these certainly do. They all form the same charge always. Magnesium is always going to be 2 plus when it's in a charged state, right? For the purposes of this class. There are exceptions to every rule, but for the purposes of what we're concerned with here, magnesium is always going to be 2 plus. It always wants to lose 2 electrons to achieve a noble gas configuration like neon. Some metals, though, particularly these transition metals in here, can lose 1 electron, 2 electrons, 3 electrons. It's always different. Okay, so we can't just call it the copper ion, right? Because it might be copper 1 plus or copper 2 plus. So for these transition metals in here, we have to add something to the naming convention. And what we add are these Roman numerals, right? Roman numeral 1 means it's 1 plus. Roman numeral 2 means it's 2 plus, right? Not that hard as long as we know our Roman numerals. Roman numeral 3, 3 plus. So for these elements in here, in the transition metals, we have to add this to our naming convention. So copper 2 plus is the copper Roman numeral 2 ion. Iron 3 plus, iron Roman numeral 3 ion. Okay, so you'll see these Roman numerals in naming compounds, and that's specifying what the charge is on that transition metal. Now, one last exception to this rule is that 3 of these transition metals, silver, zinc, and cadmium, we don't have to use Roman numerals for, even though they live in this transition metal sector here, right? Those are the 3 transition metals that we don't use Roman numerals for. Why? Because like these other elements, they only have 1 charge state. Silver is always +1, memorize it. Zinc is always +2, memorize it. Cadmium is always +2, memorize it. So if you're naming cadmium 2 plus, it's just cadmium ion. You don't need the Roman numeral because there's no ambiguity here. It's always 2 plus. Copper can be 1 or 2 plus, so I have to use the Roman numeral. That's positively charged ions. Negatively charged ions, we just change the suffix. So for positive like magnesium, it stays magnesium. But for negative like bromine, we change the suffix and it becomes bromide. Chlorine becomes chloride. Chlorine, fluoride, iodine, iodide. Right? You can do this with other elements as well. Let's look at O2 minus, oxygen, oxide. Sulfur, sulfide. Nitrogen, nitride. Okay, so it's a little bit, different with negatively charged ions or anions. We change the suffix to IDE. Positively charged ions, we don't add a suffix. Positively charged ions, we might add a Roman numeral if the elements are one of these transition metals. Lastly here for this lecture is polyatomic ions, right? These again are the groups of ions or groups of atoms that together have a charge, right? So many atoms with a charge, polyatomic ion. Most of these are anions or negatively charged. There are some positively charged ones. Okay, so here's a positively charged one. NH4 overall has a plus state, and this is ammonium. For the purposes of my class, I usually provide this table, although as you go up to more aggressive chemistries, you're expected to memorize several of these. Okay, so depending on what class you're taking, you might have to memorize these. Okay, so most of these polyatomics are some atoms along with oxygen. So a lot of times they're called oxyanions, right? Kind of like we had the oxyacid when oxygen was involved. A lot of these use the ate or ite suffix, and this will become important later when we go to naming acids in some of these compounds. Okay, so just recognize that you may have to memorize some of these, not for my class, but you may have to memorize them if you're not taking the class with me. So that does it for this lecture where we classified ionic, molecular, and acids, and then further talked about positive and negative ions and how we name those. So as always, if you like this video, feel free to like it or subscribe to my YouTube channel, right? Or as always, feel free to check me out where I do office hours every week over on Twitch and can answer any chemistry questions you have, or check out some of my other videos. That's all for today. See you next time.